as you could see right here, we have the input signal, we have this Fourier transform, that's this fast Fourier transform, and then we have a spectrogram right here. These two signals represent the sine wave and the cosine wave. That's the sine function and the cosine function. The reason why we plotted this and put this out here is because we are going to use it a lot in explanations for the Fourier transform. Now we're supposing that we have the signal right here, which we shall call f of t. Now note that a signal like this audio signal we have here is similar to what we obtain here. The difference is that the reason why we have this signal which looks kind of choked up right here and that this one looks kind of loose is that the frequency of the signal is way higher than that of this. Now let's explain this concepts clearer. So supposing we have this signal right here. So here we have this axis, which is our time. Now putting this out like this is what we call our f of t. So here we have sine t, which is our f of t, and then this is our t axis right here. Again, here we have our cosine of t axis, and then here we have our t axis. Another reason why we have this two functions very popular when it comes to audio data is because once we speak, we actually produce sound waves which take up a sinusoidal form. So in this case we have this sine function, in this case we have the cosine function. Now as we had seen in the sound wave generated, we had a very high frequency. Or we said that we had a high frequency or a higher frequency as compared to this plots of the sine and the cosine function. Now let's explain the concept of frequency. Basically, if we have this function, say if we have the t, we have sine t, that is y equals sine t. Now generally we tend to, instead of writing y equals sine t, we prefer to write y equals sine 2 pi f t, that is sine omega t. Now saying y equals sine t is just a specific case. That's a case when omega equals 1 or 2 pi f equals 1 or f equals 1 divided by 2 pi. But a general case will be simply y equals sine 2 pi ft. Now saying that y equals sine 2 pi ft means if we are given a function, say y equals sine of say 6 pi t. So if we have a sine of 6 pi t, it simply means that our f is equals 3. Since if we have to compare 2 pi and 6 pi, or if we have to compare, if we say 2 pi f equals 6 pi, then it means f equals 3. So in that case, the frequency of the sound wave represented by y equals sine of 6 pi t is 3. Now, what's the concept of frequency? What's it all about? If we look at the sine wave right here, if we fix, let's say we fix this point. Now we ask ourselves, when next are we going to meet this exact same point? We see clearly that is this, because as we could see, all the other points are different from this point. So the next time we meet, or the next time we get this exact same point is here, next time we get this exact same point is here, and so on and so forth. Now note that we could fix another point. We could fix this point right here. The next time we get this exact same point is actually here. So you may be tempted to think that's this, but not, because actually when we are this, our wave is going downward. So if we consider this about positive direction, here we're going downward, whereas we're supposing that we're going upward. So this is our point here. Next time we meet is this point. Now to get the frequency of this signal, actually we ask ourselves a simple question: what is the time taken for us to get, or for us to leave from this point to this exact same point again? So this time difference is what we call a period, and then the frequency is simply equals 1 divided by that period. So that's it. Frequency is 1 divided by the period. Again, the period is simply the time for us, or for this point to meet again, or for us to obtain this exact same point. So this distance, or this time difference we can see here, is the same as this time difference. This time difference is going to be the same as this time difference right here, the same as this time difference right here. Now, another way of defining the frequency is saying the number of oscillations we make in 1 second. Now, what do we consider an oscillation? If we fix ourselves to be at this point right here, the next time we meet the same point is at this. An oscillation now is this. So this is what we consider an oscillation. So the number of these oscillations we have in 1 second is the frequency. So it makes sense to say that if we have a very high frequency, suppose our frequency is say 10, it means we're going to have, instead of just one oscillation like this, so let's suppose that this is actually 1 second right here. Suppose that this is 1 second. It means the frequency of this signal is simply equals 1. Now, if our frequency goes to 10, it means we're going to have 10 of these. So if I have this point here, I'm going to have to do this. You see, I have to get to this point one time, the second time, and all of that 10 different times before getting to this. So in that case, I will say my frequency equals 10. Now let's take this, let's come to this point here. Let's suppose we're doing this before getting to this. So let's say we have this. Let's do that again. Now after doing that 10 times, we start to understand the choke up nature of the plot we got from the data set, which was this right here. And this tells us clearly that the number of oscillations we have in 1 second are way more than the number of oscillations we obtain in 1 second when dealing with this signals right here. So now that we've understood this concept of the frequency, we now understand clearly why it's very useful for us to know the frequency of our signal, and why also when representing the signal, for example, this Y right here, it suffices to have this frequency in here. So once we say we have a particular frequency, we've defined already that signal because we already know the number of oscillations it's going to do in 1 second. And if we know that number of oscillations, it also means we know the time taken for us to do one oscillation, which is known as a period. Now the period and the frequency are of the same importance, since once we have the period, we have the frequency, and once we have the frequency, we also have the period. Now this also goes same for the cosine function, and that's it. So we get back to our audio signal, which is our f of t right here, and then we're wanting to obtain our Fourier transform of this signal. Recall that data representation is very important, and we shall see the importance of the Fourier transform shortly. For now, let's take this definition. We have, if we have a function f of t to obtain this Fourier transform in terms of omega, recall omega equals 2 pi f, where f is the frequency. To obtain this Fourier transform in terms of omega, we simply integrate this f of t times e to the negative I omega t dt, where we move from negative infinity to positive infinity. The I here is such that I squared equals negative 1. Now, before continuing with this Fourier transform, let's look at some complex number theory. Suppose we have a complex number z, which is equals x plus iy. This I is the same I we have here. Now this I square, or this I is such that its square is equals negative 1. So we have z equals x plus iy, which is equals the real part of z. Now this x is a real part because, as we could see clearly, this is a real number. So we have the real part of z plus I times the the imaginary part of z. So we know the I square equals negative 1, and then we could represent this on an eigen diagram. The eigen diagram is such that we have the imaginary part, which is some sort of y-axis, and then we have this real part, which is some sort of x-axis, but they aren't exactly the same. So right here we have this, and then we have this point in our eigen diagram, which is a complex number. It's represented by, or we could have this complex number here given to us as z1 equals x1 plus iy1, and this complex number right here given to us is z2 equals x2 plus iy2. Now a complex number actually has a magnitude and an angle, which we shall call its phase. So we have the magnitude or amplitude, and its phase. So right here, this distance from the origin to the point, or to this point right here, is the amplitude or the magnitude, and then this angle subtended right here is its phase. So its phase here is the arctan of y1 divided by x1. And then we have something similar for this, where we have now the amplitude of, for this point here, is going to give us x2 square plus y2 square, all of that square root. So that said, we can rewrite our z as r cos theta plus I r sin theta, where x can be given to us as r cos theta and y as r sin theta. So this is the case where we have the magnitude r and we have its phase theta. So once we have this two information, we have actually the same value, or from this we could obtain the values for x and y, since we have its amplitude and its phase. So this is how we represent z in as trigonometric function, and then we could also represent z as an exponential function. So this is exponential form, a strict form, and its Cartesian form. For the exponential form right here, we have this r, so r magnitude, and then we have theta, our phase, so we have r e I theta. And that said, if we compare these two forms right here, that's r cos theta plus r sin theta, that's a trig form, with the exponential form, given that they are the same, because we say this is z and then this is z, then this implies that r e I theta equals, we factor out r, so we have cos theta plus I sin theta. Now, if we have to turn the theta to negative theta, then we will obtain r e to the negative I theta. But in this expression right here, everywhere we made theta, we have to replace with negative theta. So we have r of cos negative theta plus I sine of negative theta. That said, we have r cos theta, because cos of negative theta is cos theta, or cos of negative x is cos x, and then cos of sine of negative x is negative sine x. So in this case, we have r cos theta minus I sine theta. So from this we have, supposing we have an f of t, that's cos of omega 0 t. So coming back to our Fourier transform, so we want to calculate or obtain the Fourier transform of this function right here. Firstly, we have this function which can be written as this. But before looking at that, just note that the reason why we had to get through all this is because the Fourier transform actually includes this complex number right here. So it's important that we understand it like this. Now we've understood it. If we get back to this, we have that r e to the I theta plus r e to the negative I theta is 2r cos theta. The way we obtain this is by looking carefully at these two equations right here, where we have r e to the I theta, which gave us this, and r e to the negative I theta, which gave us this. So if we have to add up these two equations, we have r e to the I theta plus r e to the negative I theta, which is this, will give us this plus this. Now r cos theta plus r cos theta is 2r cos theta, and then r I sin theta minus r I sin theta is 0. So that's why we have this plus this giving us 2r cos theta. Now that said, it means r cos theta, which in this case is our f of t, because, or if we modify this theta, so if we turn this theta now to omega 0 t, in that case we have that f of t is this. So we've converted theta to omega 0 t, so we have now f of t, which is e to the I, or we could say e to the I theta plus e to the negative I theta. That's just from this equation right here, because we've made cos theta substitute the formula. Then we have that, so we have e to the I omega 0 t plus e to the negative I omega 0 t divided by 2. Now we have this. We can now replace to obtain this Fourier transform. We have f of omega is equals the integral of e to the I omega 0 t plus e to the negative I omega 0 t divided by 2. All of that times e to the negative I omega t dt. So there we go. So f of t is our cos, and this is what we have in the formula initially. So having this now, if we multiply here, we have e to the I omega 0 t, because this is a plus here, so we could simply integrate this separately. You could check out our course on calculus to see how this, or to better understand all those concepts if they are new to you. So right here we have this divided by 2 times this. So basically we're just breaking this up into 2 parts. So the first part, we have e to the I omega 0 t divided by 2 times e to the negative I omega t. Applying laws of indices, we have e to the negative I into omega minus omega 0 times t dt. That's this times this gives us this, and then this times this gives us this, because we're taking negative out. So we have omega 0 plus omega t, then we have dt. Now the half is taken out, so it halves all this. Now for the next step, we obtain the Dirac of omega minus omega 0 plus the Dirac of omega plus omega 0. And this can be represented as this. In order to understand how we obtain this from this integral, or this sum of the two integrals right here, let's go back to the definition of an integral. Suppose we have this axis, then we have this function, which is this one here. The area under this curve, which is this, where we take the values of x to range from a to b, is simply the integral from a to b of, suppose y equals f of x is going to be the integral of a to b of f of x dx, which is this. Now if we understand this and we recall that e to the negative I of whatever, say theta, as we had seen previously, which was actually here, we have seen that here, e to the negative I theta as cos theta minus I sine theta. So it means that this e to the negative I theta can be broken up into 2 parts. That's the cos theta and sine theta. Now if we look at the cos theta and the sine theta functions, we'll see that if we had to calculate the area under these curves as we go from negative infinity to positive infinity, then whenever we have a value which is different from omega, so suppose we have a value omega 0 equals 0, so we have let's not even specify 0, let's take any value which is different from omega, such that, or different from omega 0. So if omega, so we're supposing omega different from omega 0, then this part can be represented as a sine function and a cosine function, as we have seen here, where we're comparing this e to the negative I omega minus omega 0 is theta, as you could see. So basically we're comparing this and this. So it means this can be written as cos theta minus I sine theta. That's this part and then this part. Now if we are to integrate this cosine function as we go from negative infinity to positive infinity, we'll notice that this area, so let's look at this. Let's see how to obtain this area under the curve as we go from negative infinity to positive infinity. So suppose we had this, so suppose this is 0 right here, the origin. Now if we calculate this area here, we'll see that this, and we also calculate this area, we continue calculating the areas, and we repeat all through like this. We'll see that if this area, for example, gives us a value of say a, then this other one was going to give us negative a. So here we have a, negative a, and when we sum up these areas, we obtain a 0. So this plus this 0, this plus this 0, this plus this 0, and so on and so forth. So whether we're going from negative infinity to a certain value, or from negative infinity to positive infinity, we are always going to obtain this 0, or the area, or that integral, to be 0. So that said, once we have omega different from omega 0, then that section, or that area, or that integral is going to be 0. And that's why we could see from here that all other portions are 0. But now when omega equals omega 0, we have this function right here turns into 1, because we have e to the negative I times 0, since omega equals omega 0. Now if omega equals omega 0, it means omega minus omega 0 is equals 0. And if it's equals 0, then all this tends to 0. And if all this tends to 0, then we have e to the power of 0, which is 1. So we are integrating now instead 1 dt. And that integral gives us a non-zero value. Now, this what we did here can be repeated simply here. It's the same process. And that's why we see that when, in this case, instead we have omega equals negative omega 0. That's the only condition for which we have this upper part here turn into 0. That's why we have here when omega equals negative omega 0 and when omega equals omega 0, we have some values. So we have this peaks right here, and then for the rest of the values we have zeros. Now what does this tell us? Recall that if we have this kind of function right here, that is, we have this sine function, and that we want to represent this sine function, we simply have y equals sine of 2 pi ft. This in fact means that this frequency actually carries the information, because once we have the frequency, we can be able to obtain the whole function. So if we have, say, sine of 8t with the frequency, we could obtain the function no matter whatever we have in here. So first we are able to get the frequency, we are able to obtain the whole function. So this frequency carries the information, and it means that all other information we may be trying to work with may not be useful, especially in the case where we have this kind of repetitive periodic function which actually basically repeats itself as we go on in time. So it's needless, say, looking at all this information when the most important information is simply this frequency right here. So this Fourier transform serves as a frequency extractor, or in this our case, an information extractor, which is very important for our models to work with as compared to working with data or working with parts of the data which aren't actually important. So it serves as some sort of filter. Now we shall see the working of the Fourier transform on a more general note. So we have had this definition right here. We could rewrite it as this: f of t times cos omega t minus I sine omega t, since we have seen this expression right here. Now that we have this, we could say it's equals this plus this, or rather minus I this. So this means that the Fourier transform has two parts. We take the function and multiply by the cosine function, and then we take that same function, multiply by the sine function, while computing the areas under the curve. To better show how the Fourier transform does the frequency or information extraction, let's take this example. Suppose we have y1, which is the cosine of 2 pi f x. So in this case, we have 2 pi, there's a year, our frequency is 5. The reason why we're doing this is so that you could see clearly the frequency, and then from that, with the making use of that, looking at this, you could understand why we have this kind of curve instead. So let's modify this. You see that when we turn this into 200, we see the kind of curve we obtain. So we'll set it back to 5. Now once we have that, what we'll simply do is we have our initial initial signal, which is this cosine of 2 pi fx, which is this one right here, and then each time we're going to multiply this with a cosine of 2 pi I plus 1. So here's the frequency, but the difference is that our frequencies are going to be changing, and as the I varies, the frequency varies, and then we obtain different plots. So when I is 0, we have obviously clearly from here we have a frequency of 1. So we multiply this function with a frequency of 1 with this one with a frequency of 5, and what we obtain is this function right here. Now once we do this, let's calculate the area under the curve, because this area under the curve actually comes back to computing the integral from negative infinity to positive infinity of f of t times cosine of omega t. So this is our f of t in this case, and then we're multiplying it with this cosine of omega t. Now note that we're just taking one part, because the e to the negative I omega t is made of both the cosine and then the sine. So let's just consider one path. The other path is going to be a similar process. So after multiplying for the first case, as we saw, we have this. We could get through the function like this, and then we start to compute these areas under the curve, as we could see right here. Computing this, then we all those different areas. Note that this happens now to be actually one oscillation, since as we start with this point, the next time we get to this exact same point is only at this level. We may feel like it's this one, but it's not this, because notice that as we go down right here, we end at this level, whereas this actually went down to this. And then if we look at this other point here, you see it goes even further below this level, whereas it's only at this point where you could see that this actually does this. So this is now repeated like this up to this level here. So basically this is our this is one oscillation. Now if we look at those areas, we see clearly that they actually cancel out each other. We have this one here canceling out with this. We see this one canceling out with this. We have this canceling out with this canceling out with this, and then this canceling out with this small part, and then this other small part. So we see that all this now gives us an area of 0. If we repeat the same process for this, we obtain the same. We repeat the same for this, we obtain the same. And now also notice that those values range from -1 to 1, yeah, -1 to 1. This one range from -1 to 1, yeah, -1 to 1. But these values right here range from 0 to 1. This tells us that no matter how we try to, first of all, we are not going to have this in the middle, because the centers here are zeros, but our center here is 0.5. So we're going to have something like this. So clearly from this, it's impossible for us to have a 0 area, because all our areas are positive. So if we calculate all these areas, we will clearly have a positive value. And when does this happen? This actually happens when the value of I, because initially we have I to be 1, 2, 3, 4, 5. So when the value of I turns into 5, or rather when it turns into 4, because this is the 0th, yeah, this 1, 2, 3, 4, 5, or rather 1, 2, 3, 4. So here we have 4, meaning that I plus 1 gives us 5. So when we have a frequency of 5, then we have this area, or this non-zero area. So basically, and that is actually true because this happens because it matches up with the frequency of this y1 we have right here. So once we multiply this 2, it gives us this positive area. And it's with this that the Fourier transform is able to select a frequency which is found in a signal like this one. So with this, it automatically catches up or sees all the frequencies which are found in this input signal. So that said, let's now modify this. So let's have this right here. Okay, so we have this. Now what we've done now is we've modified this such that we have an additional, let's take this to be say 2. So we have the sum of this 2 inputs. So this inputs now is not just a cosine, but now it's a cosine and a sine, or rather a cosine and a cosine, but with 2 different frequencies. And running that, clearly we see that we have this input now, which is a mixture of the 2 frequencies, and it goes from -2 to 2 instead of -1 to 1, because we have this mixture of this signal and this signal. So having this input signal now and multiplying it with this different cosines right here, we obtain this results which we get here. We notice that from the onset we have this value, or we have the signal here, unlike previously where we only had one of the signals, which was when the frequency matched up with this 5. Now we have when I equals 1, we obtain a frequency of 2. That 2 matches up with this, so we are able to detect that this area here is different from 0. So it means that we are able to detect that this input signal contains a frequency of 2, simply from the fact that this area is different from 0. It means that this Fourier transform will be such that at the point where the frequencies match, or at the point where we have a frequency of 2, when omega equals, or when omega is such that the frequency is equals 2, then we're going to have a non-zero value. If you look at this other points here, you see -1 to 2. If we obtain the areas, we obtain 0. This one, you see, obtain 0. This one again, you see that when we have a value of 5, because this is 0, 1, 2, 3, 4. 4 plus 1, 5. You see, it gives us this from 0 to 2. This is positive, so this this position and this position are going to give us two non-negatives, or rather, it's going to give us two non-zeros. Here again, we have a 0, here 0, here 0, here 0, and finally here 0. So that's it. That's how the Fourier transform, or with the Fourier transform, we are able to detect or extract useful information like the frequency from our input signal. To generalize what we just got here for the cosine function, we have, if we have this function f of t, which is cosine of omega 0t plus cosine of omega 1t up to cosine of omega nt, meaning that we have n different frequencies, or rather n plus 1 different frequencies, omega 0, omega 1, omega 2 up to omega n, which we have to extract. Then the Fourier transform of this is a half of the Dirac of omega minus omega 0 plus Dirac of omega plus omega 0 up to Dirac of omega minus omega 0 plus Dirac of omega plus omega 0. Now we could see clearly from this that this Fourier transform is similar to what we had here. Now for omega 0, if we have omega 0 at this point, then omega 1 will be followed, omega 2, and right up to omega n. Then if you look at this fast Fourier transform of this audio signal, we also notice that the values range between 0 and 20,000. And that's because audio signals, or human sound signals, that's audio produced by humans, have frequencies ranging between 0 and 20,000 hertz. That's why you notice that between 0 and 20,000 hertz, we have all these peaks, and then from this we start having values which are practically 0.